All right, so today we are taking a look at section 4.5. It is all about derivatives and the shape of a graph. All right, and so today's what we know is going to be a little bit longer, but I think it'll be a good review of things that we've seen in previous chapters. Excuse my dog. Things that we learned in previous chapters so that we can use that to build upon knowledge that we are about to learn, okay? So let's get started with our what we know. All right, so consider a particle moving along the t-axis. So I'm gonna go ahead and put a t over here. So we know that is representing time. With the function s of t equals 2t cubed minus 14t squared plus 22t minus 5 over the interval 0 to 5. All right. And so if I were to continue to label the axes, what should I label my y-axis as? Yeah, exactly. We're going to go ahead and label this our s of t. And our clue for that is that they tell us that this is the function of not speed, but position. All right. And so we could say position, we could say s of t, we could say x of t, but all of those things just represent the position of the particle. Like, where is that particle with respect to time and a center point? All right. And so let's go ahead and take a look at some things that we know from the graph. Okay, so I'm wondering if we can answer this question: when is the particle moving to the right, moving to the left, and at rest based on the graph? And the key thing that I want to point out here is I'm asking us, when is it moving to the right, moving to the left, and at rest? Okay. So I'll go ahead and set up this part while you look at the graph and think, and perhaps type some answers in the chat. You are always welcome to, that's not how you spell rest. You are always welcome to message me directly. If you would prefer that your answer not be in the public chat, that is fine. Right, but what do we have here? When is that particle moving to the right, moving to the left, or at rest? Right, I see a few answers coming in. Don't be shy. It's okay to look back at that section in your notes too. All right. And it's okay not to answer the questions in order, right? It's okay for us to think about which ones that we might know and use that to sort of answer things, okay? All right, so we've got a bunch of answers here. One that I see that I think is most accessible to everyone is, when is that particle at rest? And so in particular, when we're thinking about when something is at rest, when something is at rest, we're thinking, where is the slope? 0. Right? And in particular, we can see that maybe right here at time equals 1, and then right down here at 3 point some decimal, we have a situation where that particle is at rest, all right? And so if I write down what I mean, I'm looking for on S of t, the slope is 0. So on the position graph, we're looking for a slope of 0. That tells us when the particle is at rest. But another way to say that is that the velocity, let's not write out the whole word, where v of t equals 0, right? When I say on s of t, the slope is 0, I am equivalently saying that the velocity is 0. And so our response would be t equals 1. And then what value did we guess it to be at? Yeah, around like 3.8-ish. All right. Does that make sense to folks that when we're looking for something, when the particle's at rest, we're looking for where the slope on s of t is 0? Okay, and so I want to be really careful about my language, because one of the things I noticed on the previous exam was we're still using a lot of pronouns like it is 0 or that is 0. And I think one of the things we're going to get ourselves into trouble with is if we're not exact with our language, we might end up reading graphs incorrectly. Okay, so a answer, if you were sort of explaining your reasoning on this, like when is the particle at rest, you could say the particle is at rest when its velocity, meaning the particle, when its velocity is equal to 0. On a position graph, this corresponds to where or when the slope is equal to 0. Okay, so I think sometimes it's hard to think about like, is my explanation correct? And this is a really good example of what I'm looking for, very specific language, because as we're going to learn in maybe like 30 minutes, if we are not specific about what we're looking for, it's going to be very hard to tell what information we're looking for. Okay, so let's see what answers we had, because I also asked you, when is the graph moving to the, when is the particle moving to the right and when is it moving to the left? And so it looks like we have sort of a mix of answers here. All right, so when we're looking for when it's moving to the right, are we looking at slope of position or are we looking at the y value of position? So I think those are two different questions. Yeah, when we're looking for motion, all right, so when we're looking for the direction of motion, this is actually looking for velocity, okay? In a very small way, it's different from the questions that we first looked at a couple sections ago. The old question was, when is the particle to the right of the center? Okay, whereas the new question is, when is the particle moving to the right? All right, and you know, it's a very subtle point, but the direction of travel, that's tied to the velocity. It doesn't matter where it is. If you are going in one direction, that will have one sort of slope, but if you move in the other direction, you'll have another slope. So if we kind of tie this back to our shuttle run or, you know, suicides, where you like start on the line, you run to the cone, you touch it, you come back. Okay, so if we think about that, maybe we draw a separate diagram here. Okay, so let's say we're all on the line, right? We're turning this calculus class into a PE class. And I'm like, I want you to all start on this line. You're gonna run this way. You're gonna touch the line over here, and then you're gonna turn around and run that way. Okay. During this first part of the exercise, in the first direction, when you're running out, you are to the right of your starting point. But your velocity in particular is positive because you are traveling to the right. But when you turn around and come back, you actually have a negative velocity because you are coming back towards the left-hand side. Okay. But in both instances, are you to the right or to the left of your starting point? You're still to the right. All right. So your position, you are on the right-hand side of your center point, but the direction of travel changes. Okay. It's kind of a weird thing to think about. But when we're looking for motion and direction of motion, we're looking for that velocity piece, okay? And so I think if we take a look at some of those other answers, for traveling to the right, we could say on S of t, the slope is what? What are we looking for? Great question. How can I tell if the first move is to the right or the left? Well, if we have a slope that is, let's see, to the right, we typically say is our like intrinsically positive direction, which I know feels weird for those folks who may be left-handed, right? That's very much a right-hand dominant society. But we're saying right now, right is sort of the designated positive direction. And so on the position, if the slope is positive, that will tell you when the velocity is positive. Okay. So anytime the velocity is positive, we actually are traveling to the right. And so if we think about where that might be on this graph, I think we could say that it corresponds to sort of this section, right? And where else does it correspond to? Where else is this particle moving to the right? Yeah, and maybe let's say from like 3 point whatever onward, right? Yeah, exactly. Now we wouldn't actually go past the 5 because we have a set interval. We only looking from 0 to 5, but everything with that positive slope is telling us that we're moving to the right. So if we wanted to use our notation, we would say including 0 to 1. Should we include 1 or not? Yeah, we should not include 1 because that has a slope of 0. All right. And so I'm not going to put a comma. I'm going to be more accurate about my notation. In union with, I'm going to start at 3.8. Do I include 3.8 or not? No, I do not. And the end of my interval is 5. And should I include 5 or not?
Yes.
Yeah, we should include that because the slope there is still positive. Okay, so I think that actually is definitely a really good conversation for us to have because everything here all the way up to 5, even at 5, that slope is still positive, right? Because if we kept going, it would still be positive. And so for that reason, we include 5. Okay, now similarly, you might be asking yourself, why would we include 0, but we don't include 1? Because at 1, the slope is not positive. But if I think about the slope at 0, that is positive, and that's why I would include it. Okay. All right, if moving to the right means that the slope is positive, then it must be that when we're moving to the left, we would want to choose the part of the function that has a negative slope. Okay, and in particular, we could say on S of t, the slope is negative. And that means that our velocity is negative. And if we were to use our interval notation here, we would say 1 to 3.8. And would we include 1 and 3.8 in our answer? No, we would not, right? We don't want to include those because those actually have a slope of 0, and 0 is not technically negative. So we got to sort of leave that out by saying, here's the parentheses, okay? Now, we've been talking about this interval notation for a while, so I hope it's clear that this is what I expect on an exam, that I do want to see interval notation. I'm seeing some people who are like, between these two values and like writing them out in words. That shows me that maybe you don't know the interval notation, so I am going to be asking that we show interval notation on the exam, okay? All right, so algebraically, because of course, this is me and I want to know, not just can you do it from graphic stuff, like here's a picture, but can we tie that to equations, right? Because the stronger the connection is there, even if it doesn't feel like it makes sense now, at some point when we have those conversations with each other or work on some assignments, the hope is that that connection becomes really tight for us, okay? So I think we can say how we would find when a particle is at rest. How would we find when our particle is at rest or given this position equation? Bingo. All right. Exactly. We're going to take that derivative, we're going to set it equal to 0, we're going to solve for t, right? We spend so much time doing that, but we want to be clear about why we're doing that. We're doing that to find when something is at rest, okay? So at rest, we could say S prime of t equals V of t. And lucky for us, this is just a power rule situation. So 6t squared minus 28t plus 22. And I'm going to want to set that equal to 0. And before I start moaning and groaning about how I might need to factor this and how it looks so complicated, one good thing to think about would be, can we find a greatest common factor? Because a greatest common factor will make our numbers smaller and therefore a little bit easier to factor, okay? So in this case, what can we factor out of here? Exactly, let's go ahead and pull a 2 out. We'll get 3t squared minus 14t plus 11 equals 0. I can leave the 2 there, or the 2, because it's just a number, I can divide that away. Okay, so whatever you feel more comfortable with, but if I had like a 2t out there, it would not be a good idea to divide the 2t away because I would lose a solution. Okay, so in this case, because t is only a number, it would be okay to say, let's go ahead and divide both sides by 2. Okay. Wow, those ones are aggressively close together. Okay, and now we factor. And this is a little bit less nice because that first value is not 1, but I think it's still a relatively quick factor. So let's take a moment, let's factor that, let's see what we get. 3t minus 11 times t minus 1. I buy that, I buy that. So 3t minus 11, t minus 1. All right. Well, that will give me t equals 11/3 and t equals 1. Okay. So t equals 11/3, t equals 1. If we look back at what we said from our graph, we expected t equals 1. We very much expected that because when we looked at our graph, we said, hey, at t equals 1, that slope is going to be 0. All right, so that corresponds to the first point we found on our graph. The cool thing is, and I think this is cool, you may not, but it was kind of hard to guess. We were like, I don't know, it's like around 4, around 3.8-ish. Turns out it is exactly 11/3, right? And so that's one of the benefits of algebraic solutions is you can actually find the exact value, whereas sometimes on a graph it's just a little bit harder to see, okay? But your answers between the two should match, all right? They should match. Now, yesterday, we kind of talked about like what we would do to figure out if slope is, if it's going to be positive or negative. And so what we're going to do right now, we're only going to do this for t equals 1, but here's what I'm going to do. I'm going to stick t equals 1 on a number line, okay? And I'm going to ask us to pick a number that is to the right of 1. And then I'm going to ask us to pick a number to the, or sorry, to the left of 1 and then to the right of 1. All right. What might be a good value to choose on the left-hand side of 1? Yeah, let's try 0. Okay. Nice, straightforward number. And here's what we're going to do. We're going to take 0 and we're going to plug it in to this equation down here. I want you to tell me, do you get a positive number or a negative number? I don't care about the number, all right? So this is going to be very familiar from when we were doing limits. And I was like, I don't care about the number. I care about the sign. And it's going to be the same thing here. I don't care about the number, but I care about the sign. All right, so if we plug 0 into here, we get negative 11 times negative 1, which does give us a positive. Yeah, that one, yep. Okay. Now, I want us to pick a number that is bigger than 1. Okay, 2, great. And we're gonna, again, not be worried about the actual number, but I want us to plug 2 into this equation circled in the red here and tell me what sign our answer is gonna be. Good, that is gonna be negative. Okay, so let's,
Excuse me.
yes, go ahead.
When I plug 1, it's not negative or positive, it's 0 for me. Because 1 minus 1 is 0, and when I multiply by 0, it's 0.
Right, but we're not plugging in 1, we're plugging in 0. We're plugging in a number to the left of 1.
Okay.
Okay.
Thank you.
But I do like that you plug, when you do plug in 1, you got 0, and that's okay. You should get 0. Why should you get 0? Because this is the velocity function. And we said the velocity at 1 is 0, right? So it should make sense that when you plug in 0, you're going to get, or when you plug in 1, you're going to get a slope of 0, right? But let's see what else we found. We found that there is a positive to the left of 0. Positive what? Well, what did we plug it into? The velocity function. This plus sign that I wrote here really means positive velocity. this negative? Well, I put the number 2 into the velocity function, and I got a negative. So that must mean that there is negative velocity on the right-hand side of 0. Okay. Now let's look back at our picture for a moment. This says positive slope to 0 slope to negative. We sort of imagine what that looks like. That is positive slope to 0 to negative. And if we think about what the picture actually looks like, positive slope to 0 to negative. All right. So this number line describes the velocity of our function. All right. And that's going to be what we learn today, is like, how do we use that number line to tell what's happening? Okay. Now, Sherwin, I love your train of thought. Because we're going to be doing other problems later, I only wanted us to put 1 on the number line right now. But another good number to put on there would be 11/3, because then you could pick a number to the left of 11/3. I bet when you plug that number into the velocity function, you would get negative. And then you would pick a number to the right of 11/3. And I bet if you plug that number into the velocity function, you would get a positive value. And if we think about what negative to 0 to positive looks like, negative slope, a 0 slope, positive slope. All right. And so this is precisely what we're going to be taking a look at today, is how do we take information about velocity and use that to tell us about a particle. Okay. So if you have a lot of questions right now, that's okay. We're going to stretch our brains even more by looking at a new kind of graph. Okay. All right. So what's new? If you have ever taken AP calculus in particular, okay? So if you took calculus in high school and it was of the AP variety, and if you sat for the AP test, then this kind of graph should actually be very familiar. But I think it's a very tricky concept to wrap our minds around. And so I want to make sure that we really take the time to unpack the meaning behind this, all right? So this says, given the graph of velocity, answer the following questions. And so we might notice here that they've already labeled the coordinates axes for us. We have a T down here for time, and we have a V up here for velocity, okay? And so it would be so important, if you are not used to reading the coordinate axes before you start answering a question, you 100% want to start doing that right now. Okay. If you don't, you're going to get very different answers that will very clearly tell me you didn't read the coordinate axes. All right. So we want to make sure we read these axes. We've got velocity, and this is a graph of velocity. Okay. So let's kind of start with these questions. They're sort of similar in structure to the ones we saw about the position graph, but I want to practice reading this new kind of graph. All right. So question A says, what is the velocity of the particle at t equals 2? And then again at t equals 7. And I want us to explain how we know. All right. So in other words, let's start with V of 2. If I asked us, what is V of 2? What would your answer be? Oh. Okay. Okay. This is good. This is good. This is the purpose of this discussion. Okay. So V of 2, here's the point, right? The slope here is actually not 0. All right. The slope here is one of these like it's not as drastic as maybe our friends who are like positive slope to negative slope. Like it's not that drastic, but it is positive slope to zero slope. Like it's a pretty abrupt change. It is pointy. So actually this point, t equals 2, is non-differentiable. Okay. However, this is not a graph of position. Velocity does not always mean slope. Velocity means slope on a position graph. But if we're not looking at a position graph, then we have to look for something different, okay? Exactly. So in this case, and this is why I'm like, please read what those axes are telling you. This is saying, I want you to go to the graph of V. I want you to go to t equals 2, and I want you to tell me what the y value is there. That's it. Okay. And so that's why I want to be really thoughtful about why we're choosing the points we're choosing. Even though it's hard to build that sort of conceptual understanding, it allows you to answer so many other questions without feeling like all you did was memorize how to do this one thing. Okay. Yeah, I think Berto's answer right there is really great. 3, because this is a velocity graph. Y is velocity, okay? And so that's going to be part of our reason. We can say that V of 2 then equals 3, all right? So V of 2 equals 3. And our reason for this would be the Y values on this graph represent velocity. Okay, the Y values on this graph represent velocity. All right, so if we answered the question V of 7, what would we say? Good, we're gonna go to 7, we're gonna find the Y value, and we're gonna say for the same reason, the Y values on this graph represent velocity. Now, I know that I ask you to explain a lot of things, and I know that it's not an English class. But if you're ever struggling in terms of, I don't know how to sort of say this, part of the reason that we write these sentences out in the notes is so that, or if I type them into the chat, I want to give you ideas on how to write, because I think that is a really big ask that I'm saying, I would like you to do this, right? Like I want us to practice this. And so it would be beneficial to maybe go back. If you're not sure how to frame something, you can always use a sentence from the notes, or you can modify that and make that your own, okay? But I will be trying very hard to make sure we use as few pronouns as possible, that we are as specific as we can be about the answer. Okay. All right, so we have our velocity graph, and we found that the Y values on this graph represent velocity, which allowed us to answer question A. All right. So the next question is this: when is the particle moving to the right, and when is it moving to the left? And so if we think about what we know, can someone, before we give answers, can someone describe to me, in general, how do we know when a particle is moving to the right? Good, good, good. So that's actually what I'm going to start with, okay? I'm going to say that the particle is moving to the right. Whoa. The particle moves to the right when velocity, when its velocity is positive. All right. Now, on a position graph, sure, we would look for slope. But this is not a position graph. What should we look for? Good, good, good. So let's add that to this, okay? So right, the particle moves to the right when its velocity is positive. On a graph of v of t, this corresponds to positive y value. Okay, this corresponds to positive y values. Now I'm going to leave that there for just a second so that we can read that, we can digest it. Because I think a lot of us have been saying, oh, if it's moving to the right, it's a positive slope. And we've made that connection in our brain. And what I'm doing right now is I'm asking you to disconnect that, insert some other words in there. And now we're looking for something different because it's not a position graph. Okay. So the particle moves to the right when its velocity is positive. On a graph of v of t, this corresponds to positive y value. Okay. And so on our graph, we can see that we have positive y values from 0 to 6, and we are not including 0, and we are not including 6. How come we're not including 0 and we're not including 6? What is the y value at t equals 0? 0. Okay. Is 0 a positive number? No, 0 is not a positive number. Okay. What about the y value at t equals 6 is also 0. And 0 is not positive or negative. Okay. And so we want to say we are from 0 to 6 is where that is traveling to the right. This would be where the slope of the tangent line on the position graph is 0. At t equals 0 and t equals 6, that is precisely where the slope of the tangent line on a position graph would be 0. Exactly, exactly. Okay. So if we modify this statement to talk about when we're looking at things on the left, all right, let's change right to left, change that right. All right, so when we are moving to the left, the particle moves to the left when its velocity is not positive, but negative. On a graph of v of t, this corresponds to negative y value. Okay. So when the particle's moving to the right, when it's moving to the left, still has to do with positive and negative velocity, but this is a velocity graph, so we get to look at different information, okay? And if we were to give the precise interval, we wouldn't say 0 to 6, we would say from 6 to 8, okay? All right, I think Abby's already hinted at the answer for part C. When is the particle at rest? Okay, here's what I would like you to do. I would like you to take one of these sentences. I would like you to modify it for, oh no, you're fine. I'm so glad that you were making that connection. I think that's so, so valuable. I want us to take either one of these sentences, either the right one or the left one, and I would like us to modify it for when is the particle at rest. Okay, so we're almost leaving a sentence frame for ourselves where we're saying these are the words that I change for the scenario, but these are the words that stay the same. Okay, so take a moment, write that down in your notes, and then I'll go ahead and write that down in our notes. All right, so right now we're taking a look at when is the particle at rest. All right, so we could say something maybe like this. The particle is at rest when its velocity is 0. Okay, so that is a great sentence that says, I know what I'm actually describing here, right? Yes, perfect. So on the graph or on a graph of v of t, this corresponds to, maybe we could say y values of 0 or x intercepts. Perfect, perfect. Great teamwork there. And if we go back to our graph, we would see that this happens exactly where Abby was talking about earlier, 0 and 6. And then if we look, there's also one more at the end. So we have 0, we have 6, and we have 8. All right, so 0, 6, and 8. And if you're like, what would this look like on the position graph? Okay, these would be the places on the position graph that have a slope of 0. Okay, in other words, this would be like the maximum or minimum of a position graph. All right, so kind of let that sort of sink into you a little bit. This would be the maxima or minima of a position graph. All right, we have one last question with this section. Then I think it'll be a good time to take a break. When does the particle have positive acceleration, negative acceleration, and 0 acceleration? All right. And I think this was kind of hinted at earlier with Alberto's comment. All right, but if we have a graph of velocity, how in the world do we find information about acceleration? Exactly, exactly. All right. So I'm just going to write out over here that if we have our position graph and we take a derivative, we'll end up with velocity. And if we take another derivative, we'll end up with acceleration. Okay. So you have position, you take the derivative, you get velocity, you take the derivative again, you get acceleration. Okay. So we are going to be looking, since this is a velocity graph, the derivative of velocity is acceleration. Well, that means that the slope of velocity is acceleration. Okay. Quick question to get you thinking about next week. Let's say I had acceleration and I undid the derivative. What would I end up with? Well, I would have velocity. Okay. Let's say I had velocity and I undid the derivative. One might even call that an antiderivative. What would I get? I would end up with position. Okay, so right now, the first half of calculus is all about this direction. Take a derivative, take a derivative, take a derivative. Okay. Today, when I put out that 4.10 video, we're going to start our journey of going backwards. Okay. So a huge congratulations is in order because we have done so much work in this direction. And now buckle up and get ready because we're going to be learning how in the world we undo all of these things. Okay. So it's just like we've been adding this whole time and now we're going to learn how to subtract. That's what we're going to be doing starting next week. Okay. But back to this question, I love that we know positive acceleration, negative acceleration, and zero acceleration correspond to the slope. And so we could say for the positive one, let's see, the particle has positive acceleration. Okay. When the slope of velocity is positive. All right. So when the slope of velocity is positive. So let's go back to our graph. We're going to practice our interval notation here. Okay. Using interval notation, where is the slope positive on this graph? Okay. I like that we know zero, we notice that it's going to be this region and this region. And so let's talk about that notation there. Okay. So is the slope positive at zero? Not the y value. What's the slope of the line at t equals 0? Yeah, this is still positive. Okay. What about the slope when we get to t equals 2? It's not actually 0. This would actually be undefined because we go from positive to 0 like so quickly, it's non-differentiable there, okay? T=4 would be another good example of a point that is non-differentiable. So it would go from like slope of 0 to negative slope so quickly, right? And so, yeah, Sophia, we're going to say bracket 0, parentheses 2. We're going to stop just short of getting to 2. Okay. Now, how do we do that for the line from 7 to 8? What is the slope at 7? Yeah, the slope at 7 is undefined. So I think we're going to go with that second answer. We're going to not include 7, but we are going to include 8. Okay. So if I go back down here, we can say from bracket 0 to 2 parentheses in union with 7 in parentheses to 8 bracket. Okay. All right, let's grab our sentence frame from the positive one. Let's go ahead and modify it for the negative one. So a particle has negative acceleration when the slope of the velocity is negative. So let's go back up to our picture. Think about interval notation. What could we say here in terms of describing when the slope is negative? Yeah, we could say 4 to 7. And I love that we've used parentheses because this whole region has negative slope, but we don't want to include 4 or 7. Exactly. We would say parentheses 4 to 7. And then if we wanted to look for where there is 0 acceleration, we could grab one of our sentences from above and modify this. 0 acceleration. So a particle has 0 acceleration when the slope of velocity is 0. And so let's figure out when that happens. And I would say exactly, the slope is 0 from 2 to 4, and we're not including 2, and we're not including 4. So just this horizontal piece right here. Exactly. So 2 to 4, non-inclusive.
There is a graph which is slightly changes at point x equal to 6. Does it influence somehow our answers? Like, can I write 4 to the 6 and then 6, 7? Should I write this?
Well, it depends what you're looking for. Are you talking about the acceleration question?
Even acceleration, should I put like 4 to 6 and then in parentheses 6 to 7?
Well, but the slope is negative the whole time. I mean, it's different kinds of negative, but it's still negative.
Okay.
Okay, so if it's the same thing happening across the whole interval, then we don't need to break it up.
Okay, thank you.
Okay, all right, great question. All right, so folks, it's been a lot of new things. Okay, hopefully maybe it makes a little bit more sense why I have been asking us to sort of explain our thinking and make sure we know what we're looking for on a graph. Okay, it's also another reason why I might have said more words before, because I wanted us to be really clear about what we're looking for depending on what the picture looked like. Okay, and that's hard to know like why that's so important until you see a different picture, and then you're like, oh, now I get it. Okay, so when we come back from break, we're going to take a look at some sort of procedures to help us figure out what a graph looks like and how we can interpret information excuse me, from a graph. Excuse me. Okay, so when we come back, let's see, it is 8:01. Let's be back at, thank you. Let's be back from break at 8:15. Okay, so we get a little bit of a stretch break. We'll come back and we'll be able to look at some theorems, and not as in depth as we did yesterday, and also revisit the sign diagrams that we saw at the very beginning of class. Okay, so I will see you folks back here in just a little bit. All right, so the example we're going to start with in the second part of class is example 1. All right, and so example 1 says sketch a graph of this function, f of x equals negative x to the 4th plus 4x cubed minus 20, using first and second derivatives. All right, so this is one way that we can apply some of that knowledge that we started to think about earlier. And what I think makes this question pretty straightforward is that I've given us some steps to follow. And so we're going to practice going through the procedure, but then when we go back to the notes, we'll really dig into like why we're doing those things. Okay, and so let's begin. Example 1, we're going to sketch this graph. Anyone have any ideas about what this looks like? Like, I know we know what x squared looks like, and some of us also know what x cubed looks like, but what about x to the 4th?
Is this like a W? Yeah.
Yeah, usually it looks like a W. It's got 3 bumps, and we might notice that there's a negative sign in front of there. And so we would expect that we end up with something kind of like this. Okay. Yeah, more like an M. Exactly, exactly. Now, this is a really great example of like why sometimes it's handy to know what a graph looks like, because you sort of have this vision in your head as you're moving along about what might make sense to find out. Okay. And so in particular, let's go ahead and follow the process for step 1. So in step 1, I say find f prime of x, find the critical numbers for f of x by setting f prime of x equal to 0 and solving for x using a greatest common factor and factoring. Okay. And so if we take our f of x as negative x to the 4th plus 4x cubed minus 20. And we were to find our first derivative, right? So we want to be really good about that notation. If we have f of x here, we want to write f prime of x down here. And with our power rule, we should see we have negative 4x cubed plus 12x squared and a 0, right? So I don't need to write that because the derivative of negative 20 is 0. And I'm finding the derivative and I want to set it equal to 0. And then I'm going to solve for x. All right, so let's go ahead. What is our greatest common factor here? Four. Yeah, 4 is possible. 4x is possible. I think 4x squared might be the best one to sort of factor out. So we're gonna have a 4x squared. All right, so greatest common factor means we want to find as much stuff as possible that we can factor out. And we're left with negative x plus 3. Okay. We go ahead and we solve. We're going to get x equals 0 and x equals 3. Okay. X equals 0 and x equals 3. Now, we've seen this process before. Find a function, or given a function, find the derivative, set it equal to 0, solve for x. And if we were to describe in words what we're finding here, we are looking for points on f of x that have a slope of 0. Okay, we're looking for points on f of x that have a slope of 0. And yesterday we talked about having critical points or critical numbers. All right, so that's where that language comes from. All right, any questions about step 1 so far? We found 2 points that might possibly have a slope of 0. All right, so step 2, make a sign diagram for f prime of x and analyze your finding. And so here's what I mean by the sign diagram. Earlier, I said, let's just draw a number line. And I only wanted us to put one number on the number line, right? So if I scroll back up to the top, the one number that we put on the number line was 1, right? But we actually had 1 and 3.8 that we could have put on the number line. So in general, you want to put all of those critical numbers or critical points on the same number line, okay? I only did one here to kind of get us thinking about that process, but in our example, we're going to go ahead and put 0 and 3. Okay, we're going to put 0 and 3. So both values that we found from step 1, we are going to put here for step 2. Okay. And we're going to use the same idea. We're going to say, let's pick a number less than 0. We're going to plug it in to our first derivative. If it's positive, we'll put a plus sign. If the velocity is negative, we'll put a negative sign. All right. Oh, yeah, like more like a whole big matrix. You have, yeah, like a whole big chart. I've seen that one too. Yeah. All right. And we're going to pick a number between 0 and 3. We're going to repeat that process. And finally, we're going to pick a number bigger than 3, plug that into our derivative, and figure out whether it's positive or negative. Okay. So if each person in the class could choose their favorite interval, and maybe we vary it so that, you know, we get all 3 intervals here. All right. And pick a number of your choice, your favorite number in that interval. You're going to plug it into your first derivative. And all you're going to tell me is that positive or negative? Okay. So let's take a moment. Let's do some computations. Let's figure out what's happening in each region. Is it positive? Is it negative? And then we'll come back and clarify what it is. All right, and whenever you found whether it's positive or negative in the chat, if you could just type the interval and whether it was positive or negative. All right, I've got a few folks saying that the interval from 0 to 3 is positive. Got a few folks saying that 3 to infinity is negative. Nice, nice. Nice. Okay, and finishing it off, that first interval was also positive. Okay. So I know sometimes it's confusing, like what the question is asking you for. And that's one of the things that, as much as, you know, the transition to online teaching has been weird and there are things that I miss, because it made me like create all these handouts, right? We have the language here. And so on an exam, you can expect similar language, make a sign diagram, and then I would be referring to this. Okay. All right, so we've made our sign diagram, and it might be nice to kind of write out like what we did here so that when we come back, we're not just like, oh, we had these pluses and minuses, like that's great. We want to make sure we remember how we got those. So we sub a number from an interval into f prime of x. Maybe I should, too many tails on my letters. All right, sub number from an interval into f prime of x. Okay. So we used our findings from step 1 so that we could have an equation to substitute things into. And now we need to do the analysis part. Okay. And so when I say analysis, what I mean is I'd like you to tell me what kind of point x equals 3 is and what kind of point x equals 0 is. All right. So to do this, I actually like to draw a little diagram to help myself. Okay. So at x equals 0 and at, what's the best way to frame this? And at x equals 3. Okay. So if I were to ask you about the slope at x equals 3, right? Like what's happening around it? I see that Matt's already put an answer in here. We have a situation where f prime goes from positive to 0 to negative. In other words, the slope goes positive to 0 to negative. And so that tells us, if we were to draw that out, we could say the slope is positive to 0 to negative, and that would give us a local maximum. Okay. I know some instructors say like you memorize what's happening here, positive to negative means it's a local max, but I find it to be maybe 10 seconds longer to say positive slope, 0 slope, negative slope, and then I know for sure it's a local maximum, right? All right, now the benefit to that, the added benefit to that is we can do the same thing for any sort of information on our number line. And so if we look at x equals 0, right, the other point of interest, if I were to draw a picture that goes with that, and I'll do that in the sort of laser pointer first, and then we'll draw it in, I'm looking for something where the slope is positive, it flattens out, and then it's positive again. So that to me would be a neither. It's not a minimum or a maximum. It's just a place where there happens to be like a resting point. Okay. So if we draw that out, we would say positive slope to 0 slope to positive slope. And then we would say that this is neither a max or a min. Okay. And so these two steps here really help us break down what that first derivative is telling us, okay? And we're gonna come back and figure out how we actually use this to graph, right? Any questions on step 1 and step 2 so far? Well, you can always ask later, but I think it's good to provide space and time in case there are questions. Let's take a look at step 3. Okay, so step 3 says find f double prime. And we're going to find the second derivative. And then I'm telling you that we're looking for potential inflection points. Now that's a new word for us, inflection points. But let's focus on the process right now, and then we'll come back and patch in like what an inflection point is, okay? So in order to do that, I probably want to grab my first derivative. And why would I choose this version of my first derivative and maybe not that second one? Yeah, it's easy to do the power rule, right? If I choose this one, I'm gonna have to use product rule. And I'd really like to make things not as complicated, right? So let's choose the version that is easier to work with. We're gonna go ahead and take that second derivative, negative 12x squared plus 24x. We're gonna set it equal to 0. And in the same step, I'm gonna look for a greatest common factor, which in this case, I hope we see as 12x. And in our parentheses, we're left with negative x plus 2. Good. All right, that leaves us with x equals 0 and x equals 2 as being these potential inflection points. Okay, potential inflection points. So just like we wrote over here, that when we found our f prime, we set it equal to 0, that we were looking for points on f that have a slope of 0. And so what we're going to describe down here is what it tells us about f of x. And it turns out that if we set the second derivative equal to 0, we are looking for points on f of x when the slope changes. Okay, when the slope changes, that is, the slope might stop getting bigger and start getting smaller. Okay. So if we were to sort of spell that out in words, this idea of an inflection point means that we're looking for points on f of x when the slope is changing. We're looking at how the slope is changing. And in particular, that is the slope might stop getting bigger or start getting smaller, or the other way around, the slope might stop getting smaller and start getting bigger. Okay. So here's what I want to do to maybe, a point where the slope changes direction. Okay. But it's not so much that the slope is changing direction, but let's maybe use a real world example to think about this. Okay. How many folks have ever heard of the phrase point of diminishing returns? Anybody ever heard that or heard diminishing returns? Yeah. If you've taken an economics class, you've probably heard about that. Anyone want to take a stab at defining what a point of diminishing returns is? All right, so we have some fancy knowledge. We have some when the marginal benefit no longer equals the marginal cost, okay? And at a certain point, your returns are getting smaller and smaller. Yep. So if you've taken econ, then what Matt says makes sense. And if you've never taken econ, maybe that's just a lot of words that you're like, I don't know what those words mean. Okay. But I think that Luca has sort of the same idea here, right? Which is at a point, whatever you're getting back is actually going to continue to get smaller for a while. All right. And so if we think about actually a cubic function is a very good example of this. All right. So a cubic function might look something like this, right? And with that cubic function, let's say that this is modeling your revenue, right? Like how much money you can make. And so you are making money, you're making money. You sort of hit this maximum. And that is the most amount of money you can make, but you're still making money at a certain point after this point. Okay, it's just getting smaller. But this is actually not the point of diminishing returns. Okay, the point of diminishing returns is actually right here. It's the point where things are still relatively good, manageable, but after that point, it's just gonna get worse. In other words, the returns will continue to diminish. They will get smaller and smaller. That might be in terms of something that we can relate to, because I don't think we all have been businesses where we are, looking at our income. If you think about studying for an exam, how many folks in here have pulled an all-nighter? Anybody ever stay up all night to study for an exam? Okay, well, you folks are way younger than I am. I can no longer do an all-nighter. In fact, if I do an all-nighter, I will be a complete mess the next day and probably for the next 3 days. That's one way to sort of frame this diminishing returns, is like in your age, right? Like at some point, it's not worth it to stay up because you just won't be able to function. But I think there's also this sweet spot where, like, if you are planning to study as long as you can into the night, right, it might be really productive and then it starts to get less productive. But there's sort of a moment where I think we realize that, like, maybe we don't realize it, but then all of a sudden we're like, I can't even read, like, I can't even write. I don't even know what I'm studying anymore. Like, nothing is coming out right. And you've sort of passed that point of diminishing returns and you've hit rock bottom, right? I like to think that this has to do with age, but it might not. I think it also has to do with people's sort of overall sense of self, that there is a point where you're not going to get a whole lot more out of it. And that comes before I fell asleep on my papers and then was like drooling all over everything, right? There's a moment in time where you still have the chance to say, I think I'll be fine. And maybe it's more important to get some sleep so that my brain works the next day. And I'm okay cutting it off here and saying that we're good. Okay. this moment before rock bottom, but after you've hit your peak, this is the point of diminishing returns. And this is what we mean when we say an inflection point. Okay. Mathematically, if we look at the shape of this first part, we might call this concave down. Okay, in other words, it's sort of like the upside down parabola. Okay. This we might call as concave up. I like to think of concave up as something that will, quote unquote, hold water. It's sort of like the way you might hold your spoon to eat cereal or soup. Because if you held your spoon in a concave down way, you would not be able to keep the soup or cereal in your spoon. Okay. This point where it changes from concave down to concave up is called an inflection point. And the way we find this is we take a second derivative. So we see where that slope stops being concave down and where it starts being concave up. Okay. So when I say, let's look for the inflection point, we're looking for where the curvature might change from this to something like this. And it could go the other way around. I could be saying this, and then at some point I'm going to start to not be able to hold water anymore. Okay. So let's come back to our question and see how we figure out algebraically, okay? Because I think that is a really interesting question. So let's see, how do we find that algebraically if the slope looks like it's going from negative to negative? Perfect, okay. So it turns out that our second derivative tells us where that slope might stop getting more negative and start getting less negative. Okay, so even though the slope is still negative, we are looking for a point where the slope stops getting more negative and starts getting less negative. All right, so we're looking for a point where the slope stops getting more negative and starts getting less negative, or a point where the slope stops getting more positive and starts getting less. Okay, that is what an inflection. And we find that by using our second derivative. So we're going to grab the numbers we found from step 3. We're going to put those on a number line. We're going to put both numbers on the number line. And we're going to use the same idea that we did for steps 1 and 2. We're going to pick numbers in this interval, in the middle one, in the right-hand interval, and we're going to plug them in to our second derivative. And let's see what we get. So let's take a moment to do some plug and chug. Remember, we're not worried about the answer, but we're worried about the sign of the answer. And let's go ahead and figure out what the second derivative is telling us about those three regions on the graph. All right, so when you get those regions and the signs, go ahead and pop those into the chat. You can do that directly to me. You can put that out to the whole group. That is your choice. All right. All right, we're getting some answers here. So far, it seems that we are in agreement that the region between 0 and 2 is positive. So for example, if I pick the number 1 and I plug that in here, I will see that I end up with a positive number. All right. If we pick 3, looks like we're going to get a negative number. Yeah. And what about the first region from 0 and like less than 0? Yeah, that's going to be negative. Okay, so it would be important to maybe just double check that before you move on, because we're using this information to create a graph. And so if this information is incorrect, your graph is going to be incorrect. All right. So if we are just really careful, double checking our numbers, we should get negative, positive, negative. Okay. All right. So that is what we consider our sign diagram. Okay. And if we were to phrase this as we did above, we could say that we sub number from an interval into f double prime of x. Okay, so we're looking to sub these numbers into f double prime of x. Now for our analysis. Okay, so for our analysis earlier, we just listed out the points, we drew a little mini picture, and then we just described what was happening. Okay, so we're going to do the same thing here. We'll have x equals 0, and we'll have x equals 2. All right. And so here's what the kind of picture that I sort of draw when I'm going through this. And so if I start with this one, at 0, this negative sign means concave down. Okay. And the positive sign means concave up. And so I'll do this in the red laser pointer first. Concave down would be something kind of like this. And then concave up would be something like this. Okay. So the picture that I might want to draw for myself is something like this, with this being the inflection point. Now, it's important to note that we have a sign change, means it goes from negative to positive. It changes. We call it an inflection point only when it changes sign. All right. Well, how might we draw a picture for this? What's happening around 2? Well, it's concave up to negative, which means concave down. And so if I draw a little mini picture, concave up would be something like this to concave down. And at that point, that will be x equals 2. That's my inflection point. All right. So before we sketch our graph, let's kind of review what we found out so far. All right. We found our critical numbers or our critical points, and we kind of talked about that yesterday. So I think it was maybe a little familiar to us. And we were able to, because we've been asking such great questions along the way, I think really connect to the idea that slope shows us whether it's a maximum or a minimum or neither. Okay. And maybe the newer parts for our brain are this part, right? Where we have this thing called an inflection point. And it's a little bit harder to see on a graph, but if we think about what it means, it's really the point where it's actually going to get a lot worse before it gets better. And so maybe it's kind of good to bail at that point and not continue, okay? How do we use all of this to sketch a graph? Well, let's see. All right. So when we're graphing, okay, I really do want us to do this by hand. All right. I can tell when you've copied a graph from Desmos because there are qualities that pop up on Desmos that do not show up in what we're talking about here. Okay, so it is very clear to me when people are copying a graph from Desmos. Don't be that person. We are going to start by marking off all of the important points that we found. Our critical numbers from step 1 and our potential inflection points from step 3. And in this case, we have 0, 2, and 3. And so we're going to mark those off on our diagram. 0 and 2 and 3. Okay, so we've got 0 and 2 and 3. And those are going to be important points on our graph where things are happening. Okay. And so maybe we start with our strengths, which might be that we know at x equals 3, there is a local maximum, right? So I'm going to go ahead and on my graph at the 3, I'm going to go ahead and put a point that is going to be higher than all the surrounding points. At x equals 0, I know that it just kind of flattens out. I don't know where the y value is going to be, and it's okay for me to put it anywhere on this y-axis. All right, so I could mark it here, I could mark it here, I could mark it here. It doesn't matter, and you're supposed to not know. Okay, you're supposed to not know. And so if we mark one here, maybe, let's say I feel like putting that critical point here, that would be fine.
What if I'm plugging in original function, the 0?
I would prefer that you don't.
Okay.
Okay, I would prefer that you don't, because that's not the important part. The important part is not, can you find the exact value? The important part here is like, can we interpret what the derivative is telling us?
Okay, thank you.
Okay. All right. The other point we want to put on here is we've got an inflection point at 2. And same thing, I don't know what the y value is going to be, but it should be somewhere between the 2 that I already drew. So maybe let's put that there. Okay. Yeah, you could put it at the origin. I think that in this case, it is likely not at the origin, right? But that's okay. You don't know. You could put it at 0, 0. That would be fine. Okay. Now, here's the important part. We want to connect the dots in a way where we use the information that we've seen above. And so I'm going to start with the maximum because I know that this goes something like this, right? I'm going to start with my strength. Maybe I don't know how to draw anything else. I'm still confused about concavity, but I know I can draw this, right? And that shows understanding. Now, to fill in the rest of them, it might be useful to look at the slope of what's happening. Up until 3, that slope is always positive, right? So if I go to my diagram and I start doing this, well, I made some of that slope negative, so that's not okay. All right, I can only go from here to here with a positive slope because that's what the first derivative test told me. I do have to make sure that the slope at 0, whatever this is flat though. Okay. Now, if I think about the inflection points, right? If I look at 0, what was happening before 0? Well, it was concave down. And so that might cause me to make something that looks like this, right? It's almost like a half a spoon that's not holding any soup. On the other side, it becomes concave up. It becomes a spoon where we are able to hold soup. In our first derivative, didn't we also find that x equals 1 has a slope of 0? No, that was in the very first problem. Our critical points here were 0 and 3. Yeah, I know. We've been skipping around a lot. I totally get that. Okay, but in our case, we only had these numbers, 0 and 3. Okay.
I have a quick question, Professor.
Yeah.
So we're using, to get like the slopes, we use our first derivative to graph it, and then just for the inflection points, we use the second derivatives.
The inflection points and whether it is concave down or concave up.
Okay, thank you.
Can you also justify this part because we know the slope is positive? Yes, you also know that the slope is positive, right? But positive slope could look like this. That's positive slope. But you know what also has positive slope is this. So to draw this part, it has to have positive slope and it has to be concave down. Okay. The next region though has to be positive slope and concave up. So we're actually looking at something kind of like this. All right. So you see how this slope is still positive. However, the concavity changed. Like now it's something that holds water or soup. And then we can just kind of connect the rest. And does that look like the graph that Desmos produces? Maybe, maybe not. But it does align with all of the information that we found. All right, so here's what we are going to do in the last little bit of time, because I want to save a little bit of time at the end of class to make some announcements about next week. All right, here's what I'd like to do. We are going to take a look at example 2. Okay, we're going to talk about example 2 for about 15 minutes. The rest of this, I will also put in a video for you with the 4.10 stuff that I'll make later today. Okay, so we will work on example 2 right now. The rest of 4.5 will be on video that will be posted later today. All right, so let's go ahead and take a look at example 2. All right, this says use the graph of f prime of x to answer the question. All right, so they are in fact telling us that this is f prime. All right. Now, if you are a person who likes to think in terms of position, velocity, and acceleration, this would be the same as a graph of what? Exactly, okay? This is really a graph of velocity. So if things make more sense to you because you're actually thinking about the direction that something's moving in, go ahead and think about it like velocity, okay? All right, this is a graph of velocity. That means all of the y values on this graph represent velocity. What does the slope of this graph represent? Good. All right. So y values on this graph represent velocity. Slope on this graph represent acceleration. All right. Whether you know this or you don't know this, well, writing this down, I think, just gives you a real solid foundation in moving forward in this question. Okay. I wouldn't try and shortcut this. I think this is a really challenging thing to shortcut. So we want to make sure that we are answering these questions appropriately. Okay. So question 1 says, where does the graph f of x have a local maximum? And I'm going to go ahead and put down the wrong answer. Okay. If you say x equals 1 is where the graph of f of x has a local maximum, I'm going to be real sad. Why is this incorrect? Okay, so that is something we really want to make sure of, that we're reading things correctly, okay? This doesn't say find when the graph of f prime has the local maximum. It says when does the graph of f have a local maximum, all right? So x equals 1 is wrong because this is the max on f prime of x, not f of x. Meaning you found the maximum of the velocity graph, not the maximum of the position graph. Okay. So how might I be able to tell where we have a local maximum on the original graph? All I have is information about the slope of the original graph. So let's go back up to the previous problem real quick. This sign diagram we built from the velocity graph, but it told us about the original graph. In particular, when the velocity goes from positive to negative, we end up with a local maximum. Where on this graph, which is a graph of velocity, does the velocity go from positive to negative? Good. All right, not at -3, but at -2. Because at x equals -3, it's positive. I want to know where it goes from positive to negative. It doesn't change from positive to negative at x equals -3. Right? This is still positive. But this, the y values go from positive y values to 0 to negative y values. Or we could say positive velocity to 0 velocity to negative velocity. Okay. And so if we write that out, we could say that f of x has a local max when v of t changes from positive to 0 to negative. Okay, that is a really important sentence. F of x has a local max when v of t changes from positive to 0 to negative. So on, and maybe let's use f prime of x instead. F prime of x changes. So on a graph of f prime of x, this occurs at x equals -2. Okay. So f of x has a local maximum when f prime of x changes from positive to 0 to negative. And on a graph of f prime of x, this occurs at x equals -2. Okay. So where I'd like to finish today is that we're going to modify what we have to answer example 2 or question 2. Okay. So where does the graph of f of x have a local minimum? Can someone tell me what I should write in red that would be the wrong answer?
-1 and 3, that's wrong.
Good, good, good. Okay. So x equals -1 and 3 are wrong because these are the minimum on f prime of x, not f of x. Okay. All right, now, if we translate the right-hand side, we might say f of x has a local min when, what's true about f prime of x? Okay, changes from negative to 0 to positive. Okay. On this graph of f prime of x, this occurs. And is there any place where the graph goes from like below to 0 to a positive? Does that happen anywhere on this graph? And I think we can see that it does not, right? And so that's okay. We know what we're looking for. We've explained what we're looking for, but on this graph, this occurs nowhere. And that's okay. All right, that's okay. I think we actually have time to do one more piece here. Let's take a look at number 3. Where does the graph of f of x have a critical point that is neither a local min or a local max? All right. So let's go back to our example here. How did we know that at x equals 0, there was neither a maximum or a minimum? All right, it went from positive to positive, the slope was still positive. And in other words, we could say that the slope didn't change, right? F prime did not change signs. So if we're looking at F prime, we had positive Y values to positive Y values. Well, let's see what's happening on this graph. Are there any places where the graph has positive Y values and then 0 and then positive? No, okay. Are there any points on the graph where the slope goes from or not where the slope, where the Y values go from negative to 0 to negative? Yeah, x equals 1. Okay, x equals 1. That is, it is a local maximum on F prime, but it's not a local maximum on F. Right? We have to be really careful about what we are looking at. Okay. So to answer this third question of where does the graph of f of x have a critical point? Okay, because we care about f of x, not f prime. Where does that have a critical point? Well, we can say that f of x has a critical point that is neither a local max or local min, when the Y values go from negative to 0 to negative, or positive to 0 to positive. This occurs at x equals 1. Okay. This occurs at x equals 1. So we are going to pause there for today, okay? But I would highly encourage you to think about this more. all right? Because it is very much something that messes with your brain. I'm literally telling you that this point right here is not a local maximum on f of x. Because we're looking at f prime of x. Okay, it's a local maximum on f prime of x, but it's not a local maximum on f of x. And that's something that takes a lot of adjusting for our brain to kind of get, okay? So it's okay if it's hard. And I know you can do it. I know you can work to understand that, okay? So let's go ahead and stop this recording.